Welcome to a lesson on conic sections. In this video we'll look specifically at circles and ellipses, but just in general, a conic section, we can visually kind of think of them as the intersection of a plane with two cones. So a circle would be formed when you took a plane and intersect it sort of perpendicularly to the cone, to one of the cones. So the cross section here is a circle. If you took a plane and intersected it with one of the cones but at a bit of an angle, that circle kind of then gets stretched, so the cross section here is an ellipse. If we kept tilting the plane, so now here if we took a plane that was actually parallel to the outside edge of the cones, the cross section between that intersection between the plane and this cone down here would create a parabola shape. And if we kept tilting it past that parallel line, so now we had a plane that was, say, maybe vertical, and it intersected both of the cones, it would actually create two curves, one at the top cone and one on the bottom cone. And so those two curves together create a hyperbola. So again, in this example, you can kind of look at a bit more of an interaction with this Wolfram demonstration. But again, so we're going to be looking at circles and ellipses on this video. And so what we want to be able to do is to graph a circle and an ellipse. We want to be able to write their equations in standard form. We want to be able to identify different characteristics of them. So for example, a circle has a center and a radius, and an ellipse also has a center, but instead of a radius it has a major and minor axes, it has major and minor vertices, and it has also something called foci. So we'll look at what those are as we move forward. Let's just start with a circle. So a circle is the set of all the points on the plane, in the xy plane, that are the same distance from a fixed point, which we call the center. If you had a point here in the middle, that's your center. So if you had a radius of a circle, so that's a fixed distance. So all the points that are the same distance, so a distance of r from that center point, all these points around here create a circle. So any point xy. Usually we'll refer to HK sort of generically as the center coordinate. So if we use that sort of an idea, then the equation of a circle, the standard equation, would be x minus h squared plus y minus k squared is equal to r squared. And again, the center is HK and the radius is r. So let's look at a few examples. So say we're given the graph of a circle and we want to write its equation down in standard form. So the two things we need is to know where the center is and then the radius. So looking at this graph here, it looks like the center is about here. So that would be at the coordinate -2, 1. And if you count from that point over to the edge of the circle, it's going to go 1, 2, 3. So I would say the radius is a 3. So our center is at -2, 1. Looks like the radius is 3. And so our equation, so it's normally x minus h. And since h is negative, it's going to be x minus a negative, which becomes x plus 2 squared plus y minus 1 squared is equal to 3 squared, or 9. Let's try and go the reverse. So if we're given the equation and we want to graph it, so again, from the equation we should be able to figure out if we have x minus 1 squared plus y plus 3 squared equals 16. Again, we should be able to realize just from the equation that the center is at 1, -3, and the radius is the square root of 16, which is a 4. So to graph this, we're going to go to the point 1, -3. And then we're going to go 4 units in the 4 main directions. So 4 right, 4 left, 4 up, 4 down, and that creates 4 points, and those are what we're going to use to draw our circle. All right, what if we're given the 2 points on the circle that are endpoints for a diameter? Well, to do this, it might be helpful first if we just look at what what we mean by the information. So we have a circle, and these 2 points on the circle represent a diameter. Now, there's infinitely many diameters depending on which way you draw it, but those 2 points just give one specific diameter. So in order to write the equation of the circle, we need the radius, which would be half the diameter, and then we need to know where's the point in the middle. So we could think of this diameter as a hypotenuse, as the hypotenuse of a right triangle. So we could think about vertically how far are we traveling, and then horizontally what's the distance. So we could think of a right triangle here. You could also use the distance formula. So if we run through the distance formula, we just plug in our x and our y values. We get the diameter has a length of 2 times the square root of 85. The radius is half of that, so the radius is going to be the square root of 85. And that means to find the midpoint, to find the center of the circle, this is the formula for the midpoint. So it's just the average of the x and the average of the y values. So if we plug those in there and simplify, we get a center of 3, 3. So we go back to our standard equation. We plug 3 in for h, 3 in for y, because that was our center, and then we're going to plug the square root of 85 in for r. And when you square root a square, it cancels, so you get x minus 3 squared plus y minus 3 squared is equal to 85.
All right, let's look at another example. This time we're given the equation of a circle, but it's in general form, so it's just all factored out. So we have 3x squared plus 3y squared plus 6x minus 12y minus 12 is equal to 0. What we should notice here first is that all the numbers are divisible by 3. So let's just divide everything by 3. That will give us x squared plus y squared plus 2x minus 4y minus 4 is equal to 0. Now to go ahead and get our equation in our format that we want, we need to complete the square. So if we first group our x's, so we'll have x squared plus 2x, and we group our y's, we'll have y squared minus 4y, and then the minus 4 will add to the right side of the equation. Now to complete the square, there's going to be a number that we're going to add to the x's to let us factor it. There's going to be another number that we're going to add to the y's so we can factor it, and whatever we add on the left side, we have to add on the right side. So to figure out what you add in both places, take the number in front of the x and the number in front of the y, divide that by 2 and square it. So we have a 2 in front of the x, so 2 divided by 2 is a 1, and 1 squared is 1, so I'm going to add a 1 on the x's. I have a 4y, so 4 divided by 2 is 2, and 2 squared is 4, so I'm going to add a 4 with the y's. And since I added a 1 and a 4 on the left, I have to add a 1 and a 4 on the right. And so that gives me the equation x plus 1 squared plus y minus 2 squared is equal to 9.
All right, let's look at ellipses. So an ellipse is the set of all points in the plane, the sum of whose distances from 2 fixed points is constant. So we call those 2 fixed points the foci. So if we have 2 foci, so this is an ellipse is sort of an elongated, stretched circle. The 2 foci are 2 points inside the curve, and it looks as if the ellipse is sort of curving around those 2 points. Okay, so those are our 2 foci, and then the distance from each of the foci to some point on the curve. Those individual distances will change, but the sum of these 2 distances will always be the same. Okay, so let's look at this GeoGebra activity here for a second, just to illustrate this. So this GeoGebra activity will sort of illustrate what an ellipse looks like. So imagine we have a piece of string that's 6.5 units long, and we attach each end of the string to a foci, to a focus point, and we put those focus points on the graph. So the total length of these blue lines together, their sum is 6.5. If we were then to put a pencil or a pen or something, a marker, up against the edge of the string, and then if we were to start moving the pencil around so that the string stays tight all the way around, Again, the total length of the string is the same, but each of those individual lengths change. So as we move around, so we're going to trace out an ellipse. And if we were to move the foci, we might end up having a different string. If we change the length of the string, we might have a different ellipse. So let's look at the equation for an ellipse. In general, the equation, and I do this a little differently than what you may see in other videos or textbooks, but I use the same equation whether the ellipse is stretched horizontally or vertically. So I have x minus h squared over a squared plus y minus k squared over b squared is equal to 1. So make sure you realize that this is a plus here in the middle. The way I have this set up, hk is still the center of your ellipse, just like it was with the circle. A represents the horizontal distance, so I always have A matching with X. A is the horizontal distance from the center to the left edge and to the right edge, and we call those the vertices. So to the left vertex and to the right vertex, from the center it's a distance of A. So here's A to the left, and here's A to the right. B is the vertical distance, so from the center to the top is B, so the top vertex, and then from the center to the bottom vertex, it's also B. And that's the same thing as if it's a vertical ellipse. A is the horizontal distance, so from the center to the right, center to the left, and then B is from the center to the top and from the center to the bottom. If A is bigger, then you're going to have a wider ellipse. If B is bigger, you're going to have a taller ellipse. And then the relationship between A and B and C, we use c squared equals a absolute value of a squared minus b squared, and c is the distance from the center to each of the focus points. So from the center to the right foci, from the center to the left foci. The foci are always on the same direction as the length of the ellipse. So horizontal ellipse will have horizontal foci, a vertical ellipse will have vertical foci. The longest length is the major axis, and the shortest length is the minor axis. So here, this is a horizontal major axis, and this has a vertical major axis. All right, let's look through a few examples. In this example, we're given the graph. From the graph, we should be able to figure out that the center is at 2, -1. The A value is kind of hard to read off the graph because it doesn't hit. Again, that's the horizontal distance. It doesn't hit a nice endpoint here. But the B value we can pick up pretty quick. The B value is from the center, 1, 2, 3, 4 units high. And the C value is the distance to the foci, which is 1, 2, 3 units high. Again, the foci is in the same direction as the length of the vertex, or of the ellipse. So we need to figure out A, so we can use c squared equals a squared minus b squared. The problem with this is it's an absolute value equation. So to solve absolute value, you have to take the 9 and do plus or minus. So a squared minus 16 is equal to plus or minus 9, which that gives you two answers. Either a is the square root of 7 or a is 5. So which is it? Well, remember, this is a taller ellipse, so that means b must be bigger than a. And if b is 4, well, 5 is bigger. So that doesn't work. So it can't be 5. So that means b has to be bigger than a square root of 7. So we know a has to be square root of 7. So if we put all that in our equation, we know the center is at 2, -1. We know a is the square root of 7 and b is 4. And we can simplify. All right, if we were given the equation already in standard form, we should be able to, again, identify some things really quick. We should be able to figure out that the center in this case is at 5 and -1. We know the a value is 2 and the b value is 3. So we still need to find c in order to find the foci. So c squared is the absolute value of a squared minus b squared. We plug in the a and the b value and we simplify. We get c is the square root of 5. So once we know a, b, and c, we can go ahead and sketch the graph. So again, the center here is at 5, -1. It goes 2 units to the left, 2 units to the right, 3 units up, 3 units down. And so that gives us the 4 points on the ellipse, the 4 vertices. And again, because B is bigger than A, it should be slightly taller than it is wide. So to find the vertices, there's 4 vertices. There's the vertices sort of on the major axis, which would be at 5, 2, and 5, negative 4. So again, these 2 points are 3 units above and below the vertex, above and below the center. And then we have minor vertices, which are 2 units to the left and to the right of the center. So now we're talking about the x value. So 3 is 2 units to the left of 5, and 7 is 2 units to the right of 5. Notice they still have the same y component, same y value as our center. The foci, again, since this is a vertical ellipse, the foci, you're going to add or subtract a square root of 5, which is our c value. You're going to add or subtract that to the y coordinate of our center, because again, it's in a vertical ellipse. The major axis is the longest, so that's 6 units vertically. The minor axis is the shorter distance, so that's 4 units across. All right, one more example here. Say we had x squared plus 4y squared minus 2x plus 16y plus 13 equals 0. We did one like this with the circle earlier, but in this case we cannot divide everything to get rid of leading terms. So let's go ahead and group our variables. So we're going to group the x's together, we're going to group the y's together, and then we're going to move the 13 to the other side. So we now need to figure out what number are we going to add for the x, what number are we going to add for the y, and then what are we going to add to both sides. And now notice here, because this is 4y squared, I have to factor the 4 out front first. So you have to factor it out of the y squared and the y term. So 4y squared plus 16y becomes y squared plus 4y. So to figure out the number we add, we take half of the 2 and square it. So 2 divided by 2 is 1, squared is 1. 4 divided by 2 is 2, and 2 squared is 4. So I'm adding a 1 and a 4. But on the right side, I'm going to add a 1 and a 16. So why is this a 16? So this one matches that one. Well, here I added a 4, but this 4 is also being multiplied by that 4. And so 4 times 4 is 16. We factor the left side. We get x minus 1 squared, and then 4 times y plus 2 squared equals 4 on the right. And then to get it in our format, we want to divide everything by 4 to get this to be a 1. And if you want, you can go ahead and practice some problems in the lab manual. This last example here was an example of a conic in general form. So it looks like this: ax squared plus cy squared plus dx plus ey plus f is equal to 0. Notice we're missing a b term, and we're not going to mess with that in this class. So if we're given this equation, and let's just assume it doesn't kind of break down and turn into a point or a pair of lines, then just looking at this equation, we can tell if this equation represents a circle, like the first one did way back, if the a and the c are equal to each other. So if, for the first example, this was 3x squared plus 3y squared, and that turned out to be a circle. We will have an ellipse if a and c are not the same, as long as they have the same sign. We will have a hyperbola if a and c have different signs, so if one is positive and one is negative. And then we'll have a parabola if either a or c is 0. So in other words, we only have one x squared or y squared. We don't have both x and y squared.